Welcome. In this video, we won't be rushing through the formulas and derivations. Instead, we will look at a particular problem that bothered Kelvin and Clausius. What exactly is temperature? Can we define it in a way that is universal and not tied to any specific substance or thermometer? We will see how that problem led quite naturally to the idea of an absolute temperature scale, the Kelvin scale. In this video, as I said, it's not about formulas and derivations. Instead, I want to focus on a specific question. What was Kelvin's temperature problem? Simply. And how did it lead to the idea of an absolute temperature scale? This is in the same spirit as our earlier videos, Newton's orbit problem leading to calculus, Einstein's relativity problem leading to spatial relativity. Here we will see how a problem about heat engine and temperature scales led to a Kelvin scale. Once we understand the question itself, then only the answer becomes something meaningful. Because this is my personal experience about this absolute uh, Kelvin scale, where the direct definitions will not be useful unless you understand the question itself. Okay. Historically, the temperature was not a very deep concept, mostly defined by how hot or cold something feels and by what particular thermometer reads. So different people used different thermometers. For example, mercury uh, is leading to Celsius and Fahrenheit scales. Gas thermometers, some scientists had suggested, which was perhaps better than mercury, and then other devices. Now, each scale chose its own fixed points, a freezing and boiling point, and its own dividing degrees. Now, these choices were convenient but arbitrary, eh, dependent on the behavior of the substance used. For example, mercury expands upon heated in one way, whereas gas expands in other way. Therefore, there is a natural question, right? Can we define a temperature in a way that does not depend on any one material, but instead reflects something universal about nature? So, here nature gave a help. For example, simultaneously in the 19th century, steam engines were at the heart of industries. Engineers and scientists were interested in a very practical questions. Given a certain amount of heat supplied to an engine, how much work can we extract? You see, being an industry, They are always interested in how efficient the manufacturing can be, right? Minimum expenditure, minimum cost. Therefore, this question. So, simultaneously, when they were looking at the temperature, industries were looking and posing this question. So, they were helping in a way. So, so this industrial question is, to be precise, how efficient can an engine be in a scientific terms? So this led Sadi Carnot to analyze so-called ideal heat engine. He imagined an engine working in a cycle, taking heat from a hot reservoir, dumping into a cold reservoir, and producing work, all in a perfectly reversible way. You see, reversible, meaning no internal friction, no losses, and in principle, the cycle can run forward, backward without any waste. We will see the definitions reversible in proper lectures that a lecture series is that he will be running. The Carnot's analysis now opened the door to thinking about temperature in a deeper and a more universal way. See how it is here. See this insight of Carnot. It, it, it gives maximum possible efficiency insight for heat engine operating between two thermal reservoirs. Because it's reversible. So then no matter what working substance you use, no matter what mechanical design you choose, there is upper limit to efficiency. In a modern language, we express this insight like for an ideal reversible engine working between hot reservoir, even cold reservoir at T2, the efficiency can be written as a function of two temperatures. Efficiency is equal to function of T hot by T cold, or you can say T1 and T2, function of two temperatures. Now, any real engine must have an efficiency less than or at the most equal to this reversible engine. The crucial point is maximum efficiency is tied only to T1 and T2, the hot source and sink, and not to any detail of the nature of the engine. This was already a strong hint that temperature is not just the number on a thermometer. See, it is connected to how much of a given heat flow in principle be turned into useful work. See the connection slowly, gradually building up. Now, this slide you will see why Carnot also used a very simple but powerful logical argument to corroborate this insight. Imagine you have two different reversible engines, both working between a hot reservoir and cold reservoir. But they are using different working systems or mechanisms or designs. So now suppose for the sake of argument their maximum efficiencies are not the same. Then what you could do is something very strange. Run more efficient engine in a forward direction. Huh? Forward means it takes heat, does some work and dumps to the sink, right? And at the same time, run the less efficient reversible. It's a reversible, you can run it backward as a refrigerator. Now you feed the some work which is from the forward engine and it pumps the heat from the cold reservoir back to hot. By choosing the right amounts of heat and work, You could arrange things such that the net effect on the reservoir is zero. So overall, they end up as they started. You see, but you have extracted net amount of heat out of the combined set of engines. In other words, you would have created a kind of perpetual motion of the second kind. You get the network output while leaving the thermal reservoirs unchanged. You see, there was, uh, we will see, and it's simply putting it right. You are doing the other way around, taking the heat from cold to hot. If this is that is what is forbidden by the second. We now regard that these machines are impossible. Is later formalized as second law of thermodynamics. See, but intuitively they all knew that this is not possible, although not formalized. So Carnot concluded all reversible engine working between the same temperature must have the same efficiency. In symbols, efficiency depend on T hot, T cold, and not on the working substance. That universality, this is universality. This is a crucial thing. Carnot had shown something very powerful. Yeah, for ideal reversible engines, maximum depends on two. So what we have seen, not on the work. Kelvin took this as a starting point and asked a very sharp question. This is what we mean here. I mean, radical thinking. Can we define temperature itself in a such a way that it depends only on how ideal heat engines behave and does not depend on which substance or which particular thermometer or so. In other words, he wanted a universal temperature scale. On this desired scale, whenever you have ideal reversible heat engine, its maximum efficiency should be expressible as a function of two numbers, T hot and T cold. That's it. And that function should be same for all reversible engine, independent of working gas, design of the engine, parameter like. So, if such a scale exists, then temperature is no longer an arbitrary reading tied to mercury or gas thermometer or their expansions, right? It becomes a quantity of fundamental, limits, quantity which is tied to fundamental limits of this energy conversion process itself. So that is what Kelvin meant, in effect, by absolute notion of the temperature. Once you accept that reversible efficiency depend only on two temperature and is the same for all reversible engines between two temperature, then the next step is very natural. Now everything follows. So Kelvin's insight was choose a temperature scale so that this universal efficiency has a simple form. Yeah, simplicity in all equations which we have established is this is the common thread. So he also came up with the simple form. So he proposed a scale on which, for a reversible engine, you just say efficiency is equal to 1 minus T cold by T hot or T2 by T1. On such a scale, the ratio T cold by T hot directly tells you what fraction of the input heat must be rejected to the cold. And 1 minus T2 by T1 or T cold by T hot is maximum possible fraction heat that can be converted into work. These are the insights. Here temperature is defined through work potential of heat flows, not just how something feels or not just numbers on the thermometer. With Kelvin's definition, temperature takes on very concrete physical meaning. So on this scale, if T equal to 0 is the point at which no further heat can be extracted to do the work in cyclic process. So absolute zero is not just very cold. You see, no, it is a thermodynamic limit. State where in principle you cannot construct any heat engine that takes heat from reservoir and converts the part into the work while rejecting the rest another reservoir uh, at even a low temperature. Not possible because T equal. So the Kelvin scale is independent of any specific substance, not anchored to arbitrary fixed points. See, like freezing point of water, but rooted in the universal behavior of reversible engines, something fundamental. So Celsius and Fahrenheit remain useful for daily life, but thermodynamics, Kelvin scale is something fundamental, as now you perhaps realize. Now, Clausius took the story step further by introducing the new thermodynamic state function called entropy. This is something remarkable uh, in the history of science. First time Clausius came up with greater than or equal to sign, mathematical, but just defining temperature scale uh, was not enough. So he actually took it further. That's the thing to consider. So for a reversible process, he defined the entropy change simply. So this is also very simple relation, but very, very insightful, very deep. ds is equal to, you can say, delta Q by T, where now T is the Kelvin temperature. This definition only makes a sense if T is absolute temperature as Kelvin proposed. See how they are linked. With this definition in place, second law of thermodynamics can be written very clearly. In any reversible process, the total entropy of the system plus environment never decreases. In a perfectly reversible process, the total entropy remains constant. So absolute temperature, capital T, is not just convenient scale. It is what allows us to write clean relationship between heat transfer and changes in entropy, and to express the directionality of the process. Now, this is very implicit direction. Uh, you will perhaps, uh, when you go forward from this basic understanding, will realize. Let's step back and see the bigger picture now. Kelvin's temperature problem began with a very practical concern. How efficient can heat engine be? Can we measure hotness in a way that is universal, not depending upon what thermometer, what working substance? That's it. The solution pushed the physics into the deeper territory. See, defining temperature via behavior of reversible heat engines and the work potential, giving absolute zero a clear operational meaning, and pairing absolute temperature with new state function, entropy, something very deeper. Uh, Not just energy, but the way energy works. So, just as Newton's questions about orbital motion pushed him towards calculus, Einstein's questions about electromagnetism and motion pushed him towards the new space-time picture. Kelvin's question about engine efficiency and temperature consistency pushed physics towards absolute Kelvin scale. In the modern form, second law. As you continue into thermodynamics, it is worth carrying Few questions with you. When you say temperature in thermodynamics, are we just talking about human sensations of hot and cold or about deeper measure of work potential? How does the idea of absolute temperature scale change your view of heat, work, and engine? Why is it important that a temperature scale not depend on any particular substance or thermometer? See, behind every neat formula, simple neat, there was a bigger problem someone had to wrestle with. Behind the Kelvin scale is a very specific problem about, sorry, for the Kelvin, the problem is universal efficiency of ideal engines. The logic that their efficiency cannot depend on the working structure and the desire to base the temperature or something more fundamental than just the column of mercury uh, happens to do or column of gas. Uh, so if you remember the story, the formulas of thermodynamics will feel less like arbitrary rules and more like expressions of nature's deeper structure.